On the right.
Okay.
Okay. The first challenge deals with a punch card encoding format. There is an hint in the subject of the challenge that gives us an indication on the kind of hardware that could be used to generate such an example. It could be an IBM model 29K punch. So this is a hardware device. It was a very popular model. With such device, a character is encoded vertically by a series of dots along a single column, and a word is encoded from left to right. Using this matching table from Douglas Jones' website, you can see the correspondence between the whole character possible in the char set on the top line and the series of dots. And you obtain the following flag. The second challenge. The second challenge is a website application written with the Django framework. A source code of an early version of this application is given to us. From this source code, we find that credentials are stored as JSON web tokens, so users are authenticated this way. If the client has a way somehow to alter such token and to make it accepted by the server, he has then the possibility to elevate his privileges and to impersonate other registered users. One possibility to do that could be, for example, to reuse the secret key available from the source code. But, well, this would not be enough, so clearly this is not the good solution. The real vulnerability is in this code extract that validates the token sent by the client. And the question is, how could we force the server to raise this exception? To answer this question, we have a look at the implementation of the GWT package in Python. And we found that the only way that doesn't depend on the format of the secret key itself appears to be this case, where there is a test for a mismatch between the announced format of the algorithm used to sign the token and the existence of the secret key as a parameter of the decoding function. Just a few words about the way a JSON web token is built. It's made in 3 parts that are separated by dots. First, there is an header which announces the kind of algorithm used to sign the token. In the second part, there is the payload, and the signature of the token is at the 3rd position. As you can see, it's quite simple, in fact, to create a new token from scratch with no signature at all, and the 3rd part of the token, in fact, is empty. In this case, the server will call the GWT decode function with our token. The algorithm is none. It will call the GWT decode function with his non-empty secret key. It will trigger the exception, and it will validate the payload, our payload, the payload we provided when we generated our token. And this way we gain access to the admin pages. The third challenge is a binary made for the Arduino platform using IVR microcontroller technology. For this challenge, we choose to use simulation to simulate this program. We used the Simavera simulator platform, and more specifically on this platform there is precisely an Arduino simulator example, so this is a good choice for us. We run the program, it provides us with a serial console, so we can interact with the program this way. When playing with it, we notice that the program immediately returns an error as soon as there is a mistake in the password without waiting that we hit the return key. So in this such circumstances, it's become trivial to guess each key of the password set by brute force independently. For example, with this very simple script, if we suppose that we already have found the beginning of the password, we send the next character, the next possible character in a loop to the serial console, and we observe the output. A bad character will generate 2 error messages from the program. A first error message from the bad character itself, of course, and an error message from the new lines of the echo command. And the good character will generate just a single error message. So we have a way to find which of these characters is the good one, and we can iterate and find the complete solution. So, thank you.
So now let's talk about the 4th challenge, which is named network, on which many of the participants have failed to solve. So when you look at the storyboard, many participants are still on this challenge. So what is it? When you access to this challenge, you get a pickup file that you can open with Wireshark, and you see a lot of packets. These packets are all TCP packets to the port 443, which is TLS. And it's like someone scan the internet for TLS connections. With TLS, what can we do? We can extract the certificates. We have some subjects of the certificates. We see that it's a scan targeted to Cisco systems. And what can we do with this? It's either steganography, where we can extract things from the packet, or it's a cryptography challenge. And in this case, it was the second case, it's a crypto challenge. From the certificate, we can get the private keys. On what can we do with when we have many private keys? We can either look for vulnerabilities like Roca or things like this, or we can simply perform a GCD, a greatest common divisor, among with all the keys, with all the private keys which are extracted. And with this, we can factorize 5 RSI keys. And once the keys are factorized, we can get the private key on the decrypt. So here's a sample Python code to build 2 keys from a found common divisor. And with the keys, we have a simple t-shirt command line that can decrypt HTTPS traffic, and in the HTTPS traffic, we get the flag. Easy. Then, we have another Catch Me challenge, which is an ARM 32-bit challenge, which asked for a password. So, let's open it with IDA, reverse it. The code is very simple. It's, you get an hash, you need to track this password. The hash is encrypted with Caesar. And if the password is correct, you get a strong function which does a lot of things. So we get the hash, we use John the Ripper, the password is winter, and when we enter winter, we get this. Whoa! So it's a really nice entrances animation. Where is it there? With this, we get another crypto challenge, which is like a pen and paper challenge. We have a tar file with two files, README and backend. The README describes a secure end circuit. Backend is a Python scripts which implement two functions about this secure end circuit, and then the README file gives a server that you can connect to, and when you connect to a server, you can probe the circuit. The circuit looks at this. It's a secure end, so you have two secret sensitive bits of information, and the goal of the circuit is to compute the end of these two bits. In order to do this, it splits each bit in 5 bits, then it computes the end of 2 bits, so the alpha 00 is A0 and B0, alpha 10 is A1 and B0. And once it computes these 25 ends, it combines them with XOR in a specific order, then it computes all the C, which are represented in the column, and then it XOR all the C's together to get the final result. Why is it doing this end in a complicated way? It's in order to perform an end which is secure with resist to 4 probes. With the server that you can connect to, you can measure 4 values out of all values which are represented there. And you can't measure A, B, and C. And the goal is to get A. Because there are 336 bits for the flag, which is 42 bytes long. And when you connect to a server, you get probes, and you get the result of a probing for each of these bits while this computation is done. So this looks secure, and this L thing in color is the way that the alpha are combined together. So there are some formulas to compute the C, and we see that it's not linear. Why does, for example, C04 is not alpha 00, XOR alpha 10, XOR and so on, XOR alpha 40? Why? Because if it was like this, it would simplify, and if it was like this, the C04 would only be A, XOR, B0. So you would only need to probe for C04 on B0, and if B0 was 1, you will get A in this C04. So that's why it's not like you sum up all the lines on the columns and you get it's an L. But with this idea, you get some formulas on doing some math. You get a simplified formula when you only need to probe 3 values, and if when you probe with this value B0 is 1, then you can get a bit of a flag. There is also another way with only 2 probes. So basically you connect to a server, you probe these 3 or 2 values several times until you get all the bits, and then you can get the flag.
Hi, my name is Sébastien Lewan, and I'm going to present you the last 3 challenges. The first challenge is called Be Ready, and is a frustrating one. We are given an executable file, which is for the RISC-V architecture. It's tiny. It's only 12 kilobytes. It's non-interactive. Actually, you just have to run it, and it will print the flag. So, let's do this. There's just one problem. Given the current state of tooling around the RISC-V architecture, it turns out running this executable file is hard. I don't have a RISC-V machine at my home, and my attempt at using emulators failed with glibc compatibility issues, which I don't want to deal with. So, what should we do? We're hackers. Let's reverse it. It turns out it was easier than to run it. So, we fire up R2 and see what we are dealing with here. We already know the program is very small. And we are lucky we have a symbol table with explicit function names like set flag, set XOR table, etc. At this point, we just have to open our RISC-V instruction set manual and translate everything into hopefully readable C code. There's only 5 functions. The first 2 ones are straightforward. They just fill arrays with fixed values. The last 3 ones do the actual computing. As you can see, it's artisanal encryption, 1 pass of patching, 1 pass of XORing, and then print flag prints the flag. So now let's just compile and run our C program, and it works. It prints the flag, which is RISC-V. No kidding. The next challenge is called the band. And there's so much to say about this one. I'm going to skip a lot of details. I'm sorry, I just don't have time. On the surface, it's a 64-bit executable file for the x86 architecture. It's pretty big, 200K, and it's interactive. It does some kind of scanf. When you run it, it asks for a string and then prints a nag error message. To make the matter worse, if you try to look at the import table, you will see that it imports lots of stuff like fork, SHM open, pipe, same weight, and other synchronization stuff, which is not a good sign. But on the inside, we discover that the user input is actually assembly code for a tiny VM. This assembly code gets assembled to bytecode and then executed in this tiny VM, which simulates the move of a cursor on a straight line. It can move left or right. There's some limits on the count of executed instructions, which is computed in a way that I'm not going to describe. And the output of this VM is the final cursor position. Actually, things are a little more complicated than that because there are 2 VM instances running in parallel. They both run the same program, which is the user input. They both share the same time limit, but they start with different initial cursor position. They are random and non-deterministic. Each time you run the challenge, you will get different initial cursor position, which makes debugging very cool. One last important point is that each VM instance knows about the initial cursor position of the other instance. Our goal is to find some programs that will cause both instances to end up on the same cursor position. We also have a constraint, which is that our program, which is the user input, must be exactly 7 instructions long. This is hard-coded, hard-checked in the program. Now let's have a look at the instruction set. It's small. 1 instruction left moves the cursor to the left, right to the right. Go to and skip next deal with the control flow. Go to is a classic relative jump. Go to -1 goes back 1 instruction. Go to 0 is an infinite loop. And go to +1 is a no-op. Skip next is the actual condition. It will skip the next instruction if, and only if, the current cursor position is equal to the initial cursor position or the initial cursor position of the other VM. Okay. What do we do here? Because I don't want to think too much. However, we know that we must write a 7 instruction long program. We have a tiny instruction set, only 4 instructions. The goto takes a parameter, but there are not a lot of values possible. Once again, we are hackers. What should we do? Let's brute force the damn thing. But not the original executable. I couldn't manage to do this. It's way too slow. So that's not a good way to do it. However, the VM is very simple. Actually, it's so simple you can even fit a complete C model of this VM on a slide. So at this point, we have something that we have control of, that we can do fuzzing on, and we just have to brute force and hoping it will get the solution. Or maybe should I say, the solutions, because it turns out there are many of them. But only one will be accepted by the GreHack website, which means you had to find a way to compute them all and then have the fun by trying them one by one and playing CAPTCHA, etc., finding pictures of cars. I need to mention one last thing about this challenge, because I want to do justice to the big engineering work that went behind this challenge. We've only scratched the surface. Because everything I've mentioned so far, from the bytecode assembler to the VM execution, all of this is not native code. It runs into another VM, a big one, which is double core, multi-process, uses shared memory, semaphores, Unix signals, lazily decompresses its instructions as they are executed, which means dumping the program is a real pain in the neck. And the native code running all of this is obfuscated with jump code. But hey, at least the code is not optimized. This last challenge is an easy one, with just one funny subtlety. We are given a small text file, which is an assembly source code for the 6502 CPU, which derivatives were used in gaming consoles like Atari 2600 and the NES. It takes no user input. Once again, you just have to run it, and it will compute the flag to a fixed memory location. To give you an idea to what assembly code for the 6502 looks like, here is an extract from this challenge. We don't need to understand this at the moment, because we just want to fire up our favorite 6502 toolchain, assemble the code, and then run it into an emulator and see what happens. And by doing this, we get something that looks like a flag, but which is not accepted by the website. What did we do wrong? The website, the GreHack website, gives us a hint. Don't always trust emulators. Sometimes they are wrong. Okay, here's the funny subtlety I was talking about. This challenge source code makes an extensive use of indirect jumps. And if you RTFM for the jump instruction on 6502.org, you will see the following. An indirect jump must never use a vector beginning on the last byte of a page. And guess what? This challenge does exactly that. Here. If you take a look at this example, you can see that the jump is jumping to the FCT1 jump vector, which is a 2-byte value, 2-byte jump vector, lying exactly across a page boundary, which is forbidden. You can see that this was made on purpose because of the org directive, which forces this invalid alignment. Okay, so it's forbidden. But so what? We want to know what happens on the real hardware. Let's have a look. let's consider the following indirect jump. Here, the programmer intent is pretty clear. We have an indirect jump to the jump vector 30ff, which lies here. So the programmer wanted to jump at the address 5080. It's Little Indian. It's a 2-byte jump vector, 5080. However, the real hardware will jump to 4080. There's a bug in the 6502, which is present in almost all consoles, which makes the hardware fetch the height byte of the jump vector 1 page too low, which means it will fetch 40 instead of 50. So, at this point, we just have to implement this bug into our favorite 6502 open source emulator and run the same assembly code again. And this time, we get a different flag, which is accepted. Which means at this point, we have all the 9 flags of this series, and we win. I'd like to end by saying a big thank you to the people who designed these challenges, because it was obviously a lot of hard work, and I had a lot of great fun. So thanks to them, and thanks for listening.